Welcome to FastAPI Part 2. In the next chapters, we go deeper into FastAPI. Chapter 6, Middleware, Dependencies, and Course Setup. Chapter 7, Async Endpoints, Background Tasks, and WebSockets. Chapter 8, Testing with pytest, TestClient, and mocks. Chapter 9, Deployment with Uvicorn, Gunicorn, Docker, and Cloud Platforms. Chapter 10, Project Structure, API Versioning, Security, and Monitoring with Prometheus and Grafana. Please consider like and subscribe if you like video. Chapter 6, Middleware and Dependencies. Reusable dependencies. In this chapter, we explore dependencies in FastAPI. Dependencies are reusable pieces of logic that we can share across endpoints. They help us avoid repeating code and make our project cleaner. Some common examples are opening and closing a database session, verifying authentication, or running extra validation before the request is processed. FastAPI gives us a tool called Depends, short for dependency injection. Dependency injection means we can define a reusable function once, and then FastAPI will handle calling it whenever we need it. Let us see an example with a function that opens a database session and another function that retrieves the current user. In this code, we first import FastAPI, depends, and HTTP exception. We create an app instance. Next, we define a function called get_db. This function simulates opening a database session. It returns a dictionary with users. The try and finally block ensures that when the request is finished, the database session is closed. Then, we define another function called get_current_user. This function takes the database session as a dependency by using depends and passing get_db. Inside, it looks for a user named Alice. Normally, in a real application, the username would come from a request token. If the user is not in the database, we raise an HTTP exception with status code 401. If the user exists, we return their information. Next, we define an endpoint at /profile. It uses depends again to automatically get the current user. Finally, it returns a greeting message with the username. Custom middleware. Middleware is code that runs automatically before and after every request. Think of it like a filter sitting between the client and your application. You can use middleware for logging requests, checking security headers, or modifying the response before it is sent back. In FastAPI, we create middleware by using a decorator called @app.middleware with the argument HTTP. The function must accept two arguments, request and call_next. The request object holds information about the incoming request. The call_next function passes the request to the actual endpoint and gives back the response. Let's see an example where middleware logs how long each request takes. Think of middleware as a wrapper around every request and response. When a client sends a request, the middleware runs first. It can inspect the request, add extra information, or block it if needed. Then it calls the actual endpoint through call_next. After the endpoint finishes and returns a response, the middleware runs again and can modify or log the response before sending it back to the client. In our function, the parameter request means FastAPI gives us the request object, which contains details such as the URL, headers, and method. The parameter call_next is a function provided by FastAPI. Its job is to pass the request forward to the next part of the application and return the response from the endpoint. We also use the keyword await because call_next is asynchronous. This means the server can handle other requests while waiting for this request to be processed, improving performance under load. By measuring the start time before calling call_next and then measuring again after the response comes back, our middleware can calculate how long the endpoint took to execute. This demonstrates how middleware surrounds the request and response cycle. It is also important to mention that response is the object returned by the call_next_request function. This object is the result of processing the request by the next part of the application, which could be another middleware or the final endpoint itself. CORS setup for front-end-backend integration. CORS stands for Cross-Origin Resource Sharing. It is a security feature built into all modern browsers. The term origin refers to the location from which a web request is being made. It's defined by a combination of the protocol, domain, and port. Imagine you have a front-end running at http://localhost:3000, and your backend API is running at http://localhost:8000. Even though both are on your computer, they are considered different origins. By default, browsers block one origin from calling another. This is to protect users from malicious scripts. But in real projects, we often need the front end to talk to the back end. That is why we configure CORS. In FastAPI, we use something called CORS middleware. Middleware is just extra code that runs for every request and response. This middleware works by adding special response headers. A header is just extra information sent with the response, almost like a label on a package. In the case of CORS, the important header is access-control-allow-origin. It tells the browser which websites are allowed to use this response. When the front end makes a request with JavaScript, the browser first checks these headers. JavaScript is the language running inside your web page that talks to the backend API. If the origin of the front end matches what the header allows, the browser lets JavaScript see the response. If it does not match, the browser blocks the response before your JavaScript code can even touch it. Some requests also include credentials, which are things that prove who the user is. The most common example is a cookie, which is a small piece of data stored in the browser to keep you logged in. Another example is an authorization header. If you decide to allow credentials, there is one important rule. You cannot use a wildcard. A wildcard is written as a star, and it means allow any origin. Browsers do not allow a wildcard together with credentials because that would be unsafe. Instead, you must list the exact trusted origins, like http://localhost:3000. Finally, before certain requests, the browser performs what is called a preflight. A preflight is a special options request sent automatically. It asks the server, what methods and headers are allowed for this resource? The CORS middleware answers this automatically, adding the correct headers so the real request can go through. In this example, we first import FastAPI and CORS middleware. We create an app instance. Next, we define a list named origins. It includes the front-end addresses that we want to allow. In this case, http://localhost:3000 and https://frontend.example.com. Then we call app.add_middleware and pass CORS middleware. We configure it with 4 options. Allow_origins is the list of origins we trust. Allow_credentials is set to true. This lets cookies or authorization headers be included. Allow_methods is set to star, which means all HTTP methods such as get, post, put, and delete. Allow_headers is set to star, which means all request headers are allowed. Finally, we define a sample endpoint at /items. When the front end at http://localhost:3000 sends a request, the server responds with the items data. The response also includes the headers, access, access-control-allow-origin, and access-control-allow-credentials. These headers tell the browser that this origin is trusted and the credentials may be used. Chapter 7. Background tasks and async features. Async endpoints and performance benefits. In FastAPI, we can define endpoints as asynchronous using async def. Asynchronous means the server does not wait idly when one task is paused. Instead, while one task is waiting for input or output, such as a database call or a file read, the server can start working on another request. This gives us concurrency. Concurrency means handling many tasks at the same time without creating a new thread for each one. It is very efficient for I/O-bound operations. I/O-bound means the task spends most of its time waiting for something external, like a database query, a remote API call, or reading a file from disk. If we wrote the same endpoint without async, the server would block while waiting for the database or file system to respond. That means other users would have to wait. With async, the server can switch to another request while the first one is still waiting. The result is better performance, especially when handling many simultaneous users. One important keyword here is await. Await tells Python, pause this function here, let something else run, and come back when the result is ready. This is what allows non-blocking behavior. So the main benefits of async endpoints are faster response under load, better scalability, and more efficient use of system resources. We start by importing async I/O and FastAPI, and then we create an app instance. The first endpoint is defined with async def and is named async_task. Inside, we call await asyncio.sleep with the argument 2. This simulates a 2-second wait, but it is non-blocking. While this function is paused, the server can process other requests. After 2 seconds, the function continues and returns a dictionary with the message async task finished. The second endpoint is called blocking_task. This one is defined with a normal def, not async def. Inside, we import the time module and call time.sleep with the argument 2. This also waits 2 seconds, but it is blocking. While this function is sleeping, the server cannot process other requests. When we test both endpoints, they look similar. Each responds after about 2 seconds, but the difference is visible under load. If you call the async endpoint while another request is running, the server can still respond to you quickly. If you call the blocking endpoint while another request is running, the server is stuck until the first one finishes. This simple example shows why async endpoints give better performance and scalability. Background tasks. Sometimes we need to perform work that takes time, but we do not want the user to wait for it. Examples include sending a confirmation email, generating a report, writing logs to a file, or cleaning up old data. In FastAPI, we can use background tasks to handle these jobs. A background task runs after the response has already been sent to the client. This way, the user gets an instant response, while the long task continues in the background. The idea is simple. We define a normal Python function for the job we want. Then, in our endpoint, we accept a background tasks parameter. We call add_task on it, passing the function and any arguments. FastAPI will run the background function after returning the response. This improves user experience. Imagine clicking a sign up button. You do not want to wait several seconds just for the email to send. Instead, the API responds quickly, and the email is sent quietly in the background. We import FastAPI and background tasks. We create an app instance. Next, we define a function called send_email. It accepts an email address, a subject, and a body. Here, we simply print a message to the console to simulate sending an email. In a real project, this function would connect to an SMTP server or a third-party email provider. Then we define an endpoint at /signup. It accepts an email parameter and a background tasks parameter. Inside, we call background_tasks.add_task. We pass the send_email function and its arguments. This tells FastAPI to schedule the function to run after the response is sent. Finally, the endpoint returns immediately with a success message. The client sees this response right away without waiting for the email to send. Meanwhile, in the server console, we can see the line sending email to test@example.com with subject welcome. This shows how background tasks make the application faster and more user-friendly by moving long jobs out of the request-response cycle. WebSockets for real-time communication. So far, all of our endpoints have used HTTP. With HTTP, communication is request and response. The client sends a request and the server replies once. After that, the connection closes. But what if we need real-time updates? For example, a chat application, live notifications, or a stock ticker. In these cases, waiting for the client to request each update would be slow and wasteful. This is where WebSockets come in. A WebSocket is a persistent two-way connection between the client and the server. Once the connection is open, both sides can send messages at any time. That means the server can push data to the client immediately without waiting for a request. FastAPI has built-in support for WebSockets using a decorator called @app.WebSocket. Inside the function, you can accept messages from the client and send messages back. This makes it perfect for building chat apps, live dashboards, and notification systems. We import FastAPI and WebSocket, then create an app instance. Next, we define an endpoint at /ws using @app.WebSocket. Inside, the function receives a parameter called WebSocket, which represents the connection with the client. First, we call await WebSocket.accept. This accepts the WebSocket connection. Then we send a welcome message to the client using WebSocket.send_text. Next, we start an infinite loop. In the loop, we wait for a message from the client with await WebSocket.receive_text. Whatever the client sends, we respond with the text "you said," followed by the same message. In this example, when a client connects to ws://localhost:8000/ws, the server greets them with welcome to the chat. If the client then sends the word hello, the server replies with "you said:" hello. Chapter 8. Testing FastAPI Applications. Unit tests with pytest. Testing is an essential part of professional software development. It helps us confirm that our code works correctly and prevents bugs from breaking the system later. In Python, the most popular testing tool is called pytest. It is simple, powerful, and widely used in real-world projects. With pytest, we write tests as regular Python functions. Each test function must start with the word test_. Inside a test, we run some code and then use the assert keyword to check if the result matches what we expect. For example, if we have a function that adds two numbers, we can test that calling it with 2 and 3 returns 5. If the result is not correct, pytest will show us a clear failure message. To run tests, we simply type the command pytest in the terminal, and pytest will automatically discover and execute all test functions. This process makes it easy to verify that small pieces of our application, called units, behave as expected. That is why these are called unit tests. Using FastAPI's TestClient. When testing FastAPI, the TestClient is one of the most important tools. It lets us simulate real HTTP requests without actually running a server. This means our tests stay fast, easy to run, and don't need extra setup. The TestClient works just like a real client, such as a browser or Postman. We can send requests with GET, POST, PUT, or DELETE, and check the responses. To read the response, we can use response.json, which gives us the parsed JSON data. We can also check response.status_code to confirm the HTTP status code. This is very useful because it allows us to test how our API behaves under different scenarios. For example, we can test that valid requests return the correct data, and invalid requests return an error code such as 404 or 422. Using TestClient, we can test both the happy path, where everything works, and the error cases, where the user input is wrong or missing. In main.py, we define a FastAPI app with a single route at /hello. This route returns a dictionary with the key message and the value hello, world. In a separate file, test_main.py, we import TestClient from FastAPI.TestClient and also import our app. We create a TestClient object based on our app. Then we define a test function called test_read_hello. Inside, we call client.get with the path /hello. This simulates a real HTTP request to our API. We then check two things. First, we assert that the status code of the response is 200, meaning success. Second, we assert that the response JSON matches the expected dictionary. When we run pytest in the terminal, it finds this test, executes it, and shows that it passed. The single dot in the output represents one successful test. This example demonstrates how pytest and FastAPI work together to test endpoints just like real client requests. As another example, in main.py, we define a FastAPI app with one route at /items. This route accepts a POST request and expects a JSON dictionary as the request body. It simply returns the same dictionary wrapped inside another dictionary with the key item. In test_main.py, we import TestClient and our app, then create a TestClient object to simulate requests. The first test, called test_create_item, sends a POST request to /items. We include a JSON body with name book and price 10. We then assert that the status code is 200 and that the response JSON matches what we expect. The second test, test_invalid_item, sends a POST request with no data. In this case, FastAPI automatically validates the request and returns status code 422, meaning unprocessable entity. We assert that this status code is correct. When we run pytest, both tests pass. The double dots in the output show that two tests succeeded. This example shows how TestClient helps us check both valid and invalid requests, ensuring that our API handles different cases correctly. Mocking DB and dependencies in tests. When testing APIs, we often depend on databases or external services. But using a real database in unit tests is usually a bad idea. It makes tests slow, harder to set up, and sometimes dangerous, because tests might accidentally change real production data. The solution is mocking. Mocking means replacing the real dependency with a fake version, so that the test can run safely and predictably. In FastAPI, we can override dependencies easily. Every dependency in FastAPI is declared with dependency injection, which means we can swap it out with another function during testing. We use a special dictionary called dependency_overrides. Here, we can assign our fake function to replace the real one. This way, when our endpoint asks for the database session, it gets our fake session instead. We can fill this fake session with test data and check if the endpoint behaves correctly. We can also mock other external services, such as third-party APIs, authentication providers, or email systems. This keeps our tests fast, independent, and safe. In main.py, we define a dependency function called get_db. Normally, this would create and return a database session. For simplicity, here it just returns a dictionary with the key user set to Alice. Then we define a route at /user. It depends on get_db. Inside, it returns a JSON object with the username, taken from the database dictionary. In test_main.py, we write a fake version of get_db. Instead of Alice, this fake returns Bob. We then use app.dependency_overrides to replace the real get_db with our fake one. This means whenever the endpoint depends on the database during the test, it will get the fake dictionary instead. We create a test client for the app and write a test function called test_read_user. Inside, we send a GET request to /user. We then assert that the status code is 200 and that the return JSON is username Bob. When we run pytest, the output shows the test passed. This demonstrates how dependency overrides let us replace real services with fake ones, making tests fast, safe, and predictable. Chapter 9: Deployment and Production. Running with Uvicorn and Gunicorn. So far, we have been running FastAPI with Uvicorn in development mode. Uvicorn is a high-performance ASGI server designed for async Python frameworks like FastAPI. ASGI stands for Asynchronous Server Gateway Interface, and it is the standard way for modern Python web apps to communicate with servers. In development, we usually start Uvicorn with the reload option. This means the server automatically restarts whenever we change the code. For example, we run the command uvicorn main:\app-reload. Here, main refers to the file main.py. App is the FastAPI instance inside that file, and reload tells Uvicorn to watch for changes. However, in production, we need more reliability and performance. That's where Gunicorn comes in. Gunicorn is a process manager. It can start multiple worker processes, handle crashes, and restart them automatically. We can combine Gunicorn with Uvicorn workers. That way, Gunicorn manages the processes, while Uvicorn handles the async FastAPI requests. A common production command looks like this: gunicorn-k uvicorn.workers.uvicorn-worker main:\app. This setup allows multiple worker processes, giving better performance and stability for real-world deployments. Here, -k specifies the worker class. We choose Uvicorn Worker, so Gunicorn runs our FastAPI app with Uvicorn. Gunicorn then manages multiple processes, improving reliability and throughput. In short, use Uvicorn with reload in development and Gunicorn with Uvicorn workers in production. Environment variables and settings. In real projects, we never want to hard-code sensitive information, like database URLs, API keys, or secret tokens, directly inside the code. If we do, it becomes unsafe and hard to change between environments, for example, local development, staging, and production. The best practice is to use environment variables. An environment variable is a key value pair stored outside the application. For example, a database URL can be stored as db_URL in the environment and then loaded into the app at runtime. FastAPI works perfectly with Pydantic for this. Pydantic provides a class called BaseSettings, which can automatically read environment variables and map them to Python attributes. We usually put this in a file like config.py. That way, all our settings are in one place, and we can easily switch values depending on the environment without changing the actual code. This keeps the app secure, flexible, and production-ready. Here in config.py, we define a class settings that inherits from base settings. We declare two fields, db_URL and API_key, both as strings. Inside the nested config class, we specify env_file equals .env. This tells Pydantic to load values from a file named .env if those environment variables are not already set in the system. At the bottom, we create a settings object which automatically reads the environment variables. In main.py, we import this settings object. We define an endpoint at /info that returns the values of db_URL and API_key. The .n file contains the real values. For example, db_URL is set to a PostgreSQL connection string, and API_key is set to supersecret 123. When we call the /info endpoint, we see those values returned in the JSON response. In a real application, we would never expose sensitive settings like database URLs or API keys through an endpoint. The purpose of /info here was only to demonstrate how environment variables are loaded into the app. The real security benefit comes from not hard-coding these values in the source code or committing them to GitHub. By keeping them in environment variables or a .nv file that is excluded from version control, we make sure only the server has access to the real secrets. This means the same codebase can run safely in different environments, while the secret values remain private and configurable. Dockerizing a FastAPI app. When deploying a FastAPI app, one of the most common approaches is to use Docker. Docker lets us package our application, dependencies, and environment into a single unit called a container. This means the app will behave the same whether it runs on our laptop, a testing server, or a production cloud machine. The recipe for building a container is written in a file called Dockerfile. Inside, we specify the base image, install dependencies, copy the application code, and define the command to start the server. Once the Docker file is ready, we build an image using the command docker build-t fastapi-app. Here, -t gives the image a tag, fastapi-app, and dot means the Docker file is in the current directory. After building, we run the container with docker run-p 8000:8000 fastapi-app. The -p option maps port 8000 inside the container to port 8000 on our machine. Now, when we open http://localhost:8000, we can see our FastAPI app running inside Docker. This approach makes deployments reliable, portable, and cloud-friendly. In this example, in the Docker file, we start with a base image Python:3.11-slim. This is a lightweight version of Python, good for production. We set the working directory to /app. Next, we copy the requirements.txt file and install dependencies with pip install. This makes sure FastAPI and Uvicorn are available in the container. Then, we copy the rest of the project files into the container. Finally, we set the command to run Uvicorn main:\app binding to host 0.0.0.0 and port 8000. This makes the app accessible from outside the container. To build the image, we run docker build-t fastapi-app. To run the container, we use docker run-p 8000:8000 fastapi-app. Now the app runs in a containerized environment, isolated from the host system, and behaves consistently in any deployment. Deploying on cloud platforms. After containerizing our FastAPI app with Docker, the next step is to deploy it on a cloud platform. Cloud platforms let us run applications at scale, manage resources automatically, and make our service available to users worldwide. There are many options: Amazon Web Services, or AWS, Google Cloud Platform, or GCP, and Microsoft Azure are the big three cloud providers. They offer full control with services like virtual machines, Kubernetes, or serverless functions. For smaller projects or simpler setups, platforms like Render or Railway are popular. They provide managed hosting for web apps, databases, and background workers, with very little setup required. The general deployment flow is the same. First, Build a Docker image of your app. Next, push that image to a container registry, such as Docker Hub or AWS Elastic Container Registry. Then, tell the platform to deploy the image. You also configure environment variables for things like database URLs and API keys, and optionally enable scaling, so the platform adds more instances when traffic grows. Once deployed, your FastAPI app is available on a public URL, securely served with HTTPS, and backed by the cloud provider's infrastructure. This is the final step to make your FastAPI project production-ready and accessible to real users. In this example, first we build the image using docker build-t my-fastapi-app. Next, we tag it for a container registry. For example, docker tag my-fastapi-app username /my-fastapi-app:\latest. Then we push it with docker push username /my-fastapi-app:\latest. This uploads the image to Docker Hub where cloud platforms can pull it. Finally, we deploy it on a platform. Each provider has its own process. For example, with Railway, we can simply run Railway up. On AWS, GCP, or Azure, we would configure a service to pull the image and run it on their infrastructure. Once deployment is complete, the cloud platform provides a public URL for our app. At that point, the FastAPI application is live, accessible to users, and running in a secure, scalable environment. Chapter 10: Extras for Real-World Readiness. Structuring larger FastAPI projects. When building small projects, you can often fit everything into a single main.py file. But in real-world applications, that quickly becomes messy and hard to maintain. The solution is to structure the FastAPI project into modules. A module is simply a folder or file that groups related functionality. For example, you may have one module for user management, another for items or products, and another for authentication. FastAPI provides a feature called routers, which makes modular code easy. You define routes for each module in separate files, then include those routers inside the main application. This keeps your code organized, testable, and scalable as the project grows. A common structure looks like this. At the top level, you have an app folder. Inside it, you place main.py as the entry point. Then you create subfolders such as routers, models, schemas, and services. The routers folder holds API route definitions. The models folder defines database models. The schemas folder holds pydantic models for request and response validation. The services folder contains business logic, like sending emails or calculating prices. By separating code in this way, you make it easier for multiple developers to work on the same project, and you reduce the risk of creating a large, unmanageable file. In this example, in main.py, we create the FastAPI application and include two routers, one for users and one for items. This way, the main file only organizes the modules, and each module handles its own routes. Inside users.py, we define a router. Notice that the router is created with prefix equals /users and tags equals a list with the word users. The prefix setting means every endpoint in this router will automatically start with /users. So if we define a route at path /, the actual endpoint becomes /users/. The tag setting is not about routing. It is used only for documentation. FastAPI automatically generates Swagger UI and redoc pages and tags group related endpoints together in those docs, making them easier to navigate. Inside the user's router, we created a simple get route that returns a list with one user named Alice. In items.py, we do the same thing. We create another router with prefix equals /items and tags equals a list with the word items. That means every route in this file will start with /items, and in the documentation, all these routes will appear under the group labeled items. We then add a get route that returns a list with one item, a book. When the application runs, the main file pulls these routers together. You can access /users to get the list of users and /items to get the list of items. The important takeaway is that prefix helps keep the API paths organized, while tags help keep the documentation organized. Together, they make a project more modular, readable, and easier to maintain. API versioning and documentation best practices. In real-world applications, your API will change over time. New features are added, old fields may be removed, and security requirements may evolve. To avoid breaking existing clients, we use API versioning. The simplest way is to add the version in the path. For example, /API/v1/users for version 1 and /API/v2/users for version 2. Older clients can continue using version 1 while new clients upgrade to version 2. This strategy keeps backward compatibility, so updates don't break production systems. Along with versioning, documentation is a critical part of building APIs. FastAPI automatically generates interactive documentation using Swagger UI and Redoc. You can see it at /docs or /redoc when the server is running. But to make that documentation truly useful, we should add details such as tags, summaries, and descriptions to our endpoints. Tags group endpoints by category. Summaries give a one-line explanation of what the endpoint does. Descriptions allow longer explanations with examples. Another best practice is to use clear request and response models with pydantic. This ensures that your documentation clearly shows the expected input and output formats. Good documentation not only helps front-end developers use your API correctly, it also serves as a live contract between teams and reduces misunderstandings. We start by creating two routers, one for version 1 and one for version 2. The variable router_v1 is created using API router. We give it a prefix of /API/v1/users. This means that every route in this router will begin with that path. We also give it a tag called users_v1. That tag will appear in the automatic documentation to group all version 1 user routes together. Next, we define a class named users_v1 that inherits from base model. Base model comes from pydantic, and it is used to define the shape of the data. In this case, the version 1 user model only has a single field, the name, which is a string. Then we define a route using the decorator @router_v1.get. The path is a /, which means this endpoint will respond at /API/v1/users/. We also add a summary and a description. The summary is a short one-line explanation that appears in the documentation. The description is a longer explanation that gives more detail about what the endpoint does. The function get_users_v1 simply returns a list with one user named Alice. For version 2, we repeat the process. We create a router named router_v2 with the prefix /API/v2/users and the tag users_v2. This keeps the routes for version 2 grouped separately in the documentation. We then define a pydantic model named users_v2. This time, the model has 3 fields: ID, which is an integer, name, which is a string, and email, which is also a string. This shows how version 2 has expanded data compared to version 1. Next, we define another route using @router_v2.get. Again, the path is a /, so this endpoint will respond at /API/v2/users/. The summary and description explain that this endpoint returns an extended list of users with IDs and emails. The function get_users_v2 returns a list with a single user object containing an ID, a name, and an email. Finally, we include both routers in the application using app.include_router. First, we include router_v1, then we include router_v2. This tells FastAPI to register all the endpoints from both routers into the main application. The result is that our app now has two different versions of the user's endpoint. /API/v1/users returns the simple model with only a name, and /API/v2/users returns the richer model with ID, name, and email. At the same time, the documentation groups them into users v1 and users v2 sections. This structure demonstrates how to keep backward compatibility using versioning, and how to make the documentation useful and easy to navigate with summaries, descriptions, and tags. Rate limiting and security best practices. When building real-world APIs, two concerns are critical: rate limiting and security. Rate limiting means putting a cap on how many requests a client can make in a certain amount of time. Without it, a buggy script or a malicious attacker could overwhelm your server. For example, you might allow each user to make only 100 requests per minute. Rate limiting can be enforced per user, per IP address, or per API key, depending on your system. FastAPI does not have built-in rate limiting, but you can use libraries like SlowAPI, or you can place your app behind an API gateway like NGINX, Kong, or a cloud provider's load balancer, which can handle rate limiting for you. Now, let's talk about security best practices. Always run your FastAPI app over HTTPS, not plain HTTP, to make sure data is encrypted between the server and the client. Validate both input and output using pydantic models. This ensures that only the correct types of data are accepted or returned and prevents accidental leaks or injection attacks. Protect sensitive data such as passwords, API keys, or tokens. Never log them in plain text or expose them through endpoints. If authentication is needed, use standards like OAuth2 or JSON Web Tokens, also known as JWT. These approaches allow secure user login and access control. Finally, apply CORS rules carefully. Do not allow all origins unless you absolutely must. Always specify trusted domains, especially if your API requires authentication. By combining rate limiting with strong security practices, you reduce the risk of abuse and keep your application reliable and safe. In this example, we are adding rate limiting to a FastAPI app using the library SlowAPI. First, we create a limiter object. The limiter uses a helper function called get_remote_address. This function extracts the client's IP address from each request. That IP address is then used as the unique key for tracking request counts. In other words, every client IP will have its own limit. Next, we attach the limiter to our FastAPI app by setting app.state.limiter. This makes the limiter available for use in decorators on our routes. Now comes the important part: handling errors when the limit is exceeded. By default, if a client makes too many requests, SlowAPI raises an exception called rate limit exceeded. We need to catch that and return a proper response. We do this with the decorator at app.exception_handler, and we pass the exception class rate limit exceeded. That tells FastAPI to call our custom handler whenever this exception is raised. Inside the handler function, we accept two arguments, the request and the exception. We then return a JSON response with the status code 429, which is the standard HTTP status code for too many requests. The body of the response is a simple JSON message telling the client that the rate limit has been exceeded. This way, instead of crashing, the server politely tells the client what went wrong. Now, we create an endpoint at /items. We decorate it with limiter.limit and pass the string 5 per minute. This means that any single client IP can only call this endpoint 5 times per minute. If the client tries a 6th request within the same minute, our handler will catch the rate limit exceeded exception and return the 429 response. Finally, the function get_items simply returns a success message saying that you can only call this 5 times per minute. This code demonstrates how to apply rate limiting in FastAPI at the application level. It protects your server from being overwhelmed by repeated requests, whether intentional or accidental, and provides clear feedback to the client when the limit is reached. Monitoring, logging, Prometheus, Grafana integration. Monitoring in FastAPI has 3 layers: logging, Prometheus, and Grafana. Logging means recording important events, like incoming requests or errors. With logging, we can check the flow of requests and responses when debugging issues. Prometheus is a tool for metrics collection. It pulls data from a special endpoint, /metrics. That data includes request counts, latency, and error rates. Grafana is the visualization layer. It connects to Prometheus and creates live dashboards that show the health and performance of your FastAPI service. When combined, logging gives detailed stories of what happened, while Prometheus and Grafana provide trends and statistics. This complete setup helps teams detect, analyze, and fix problems quickly. Let's carefully break down the monitoring code. First, we import the required modules. We bring in FastAPI and request to handle the web application and incoming requests. We also import logging from Python's standard library and instrumentator from the Prometheus FastAPI instrumentator package. This package gives us easy integration with Prometheus metrics. Next, we configure logging. The call to logging.basic_config sets the logging level to info. That means only important messages like info, warning, error, and critical are shown. Debug messages are ignored. The format tells Python how each log line should look. Here we include the time, the severity level, and the message. For example, a log line might look like 2025-09-25-12:30:15 info, incoming request. This makes logs consistent and easy to read. We then create a FastAPI app as usual with app equals FastAPI. After that, we add a middleware function called log_requests. Middleware in FastAPI is a function that runs before and after every request. It takes 2 arguments, the request object and call_next. The request object holds all information about the incoming request, such as the method and the URL. Call_next is a special function provided by FastAPI that lets the request continue to the next stage, which could be another middleware or the actual endpoint. Inside this middleware, we log the incoming request by printing its method, like get or post, and the URL. Then we call await call_next to let FastAPI handle the request. We await it because the processing is asynchronous, meaning it may take some time. After the request is processed, we get a response object back. This response is what will be sent to the client. We log its status code, for example, 200 for success, or 404 for not found, and then return it. Next, we integrate Prometheus monitoring. The instrumentator class is a helper that automatically collects metrics about requests and responses. The instrument method attaches these metrics to the app. The expose method creates an endpoint at /metrics. When Prometheus visits this endpoint, it receives data like total number of requests, request durations, and error counts, all in a format Prometheus understands. Finally, we define a simple root endpoint at /. It just returns a JSON message, hello with monitoring, This endpoint is not about monitoring itself. It just proves that our app works and can be monitored. To summarize, the logging setup ensures that every request and response is written to the logs, which helps with debugging. The middleware makes that possible. The Prometheus integration makes metrics automatically available, and Grafana can later visualize those metrics in dashboards.
Thanks for watching.